Yep. Good evening, everybody. My name is Suraj. My research is on inflationary cosmology, potential solution to flatness and horizon problems of the cosmic microwave background. Now, in any discussion, when we speak about cosmology or the CMB, we begin that discussion with the Big Bang Theory. The Big Bang Theory is a set of descriptions detailing the universe from an extremely tiny, extremely dense, and extremely hot universe to the enormous cosmos that we see today. Now, these set of descriptions, these aspects of the Big Bang Theory have been proven by many experiments, from astronomical observations to particle collider experiments to theoretical supercomputer models. And yet there remain certain parts of the theory that have still been unverified and require more evidence. So let's begin with the irrefutable, the overwhelming evidence that we have. When the universe was just under 400,000 years old, the hot plasma began to cool down and the first hydrogen atoms began to form. It was these neutral hydrogen atoms that were unable to absorb thermal radiation which escaped that patch of the universe. Thus, the universe went from being opaque to becoming transparent. It was this infrared light that escaped the universe that gravitationally redshifted into the microwave background that we detect today here on Earth. Now you can see that through the sensitivity of our detectors, the evolution of the sensitivity, I should say, we've improved tenfold from COBE to NASA's WMAP to ESA's Planck satellite, which remains to be the highest resolution mapping of this radiation. Now you can think of the CMB as like a fingerprint of the early universe. Much of our data, much of our information that comes from physical cosmology and features and parameters of the universe come from these data sets of the CMB. There's a host of information from temperatures to curvatures to mass density to density fluctuations, all imprinted in this one radiation of light. It's pretty remarkable that we can do this. So what problems then do we have in making a topology of the universe, in creating our understanding of the early universe? These problems are the flatness problem, the horizon problem, the magnetic monopole problem, why we don't see these monopoles in the universe, and of course the mysteries of dark energy and dark matter, and finally the baryonic asymmetry problem. Why does matter have an existential preference over antimatter, and why that disparity exists in that universe? In my research, I'm going to limit myself to the flatness and horizon problems. So the flatness problem is talking about the shape of the universe. What is the overall structure and shape of the universe? Now, according to Einstein's GR, mass density affects space-time geometry. So here we use the Friedmann equations, which help us put a picture on the put a shape of the universe, if you may. So the second equation that you see here is like a rearrangement of the first Friedmann equation. On the left-hand side, you see the omega symbol. That's the density parameter. It's a ratio of two densities. It's the ratio of the observed density divided by a critical density. It's this critical density that dictates the shape of the universe. And you can see its effect on the right-hand side, where k kappa is the spatial curvature term, and a is the scale factor. How is the universe scaling based on the mass density inside it? Now, interestingly, is this density parameter omega, if it's less than 1, we say there's the negative curvature. The universe is folded in on itself, and we live in an open and infinite universe. If it's greater than 1, on the other hand, we live in a positively curved surface, one where angles of a triangle sum up to greater than 180 degrees, one where two parallel lines will eventually intersect, and the middle ground between those two worlds is a flat universe. Now, the interesting part about this theory is that we can actually empirically observe and calculate the omega value and therefore deduce the shape of the universe. And we can get this omega value from the CMB, where data of the entire early observable universe is. And that's exactly what the Planck team and the Planck satellite did, and here are the results. These are known as the cosmological parameters, makes up everything in the universe, and it's from these results that physicists famously conclude that dark energy is made up of 70%. Dark energy makes up 70% of the universe, and as you can see, dark matter makes up 25% of the universe, etc. And if you add up all these cosmological parameters, you get a full and final value of the omega, which we can put in the Friedmann equation and deduce the shape of the universe. So interestingly, when you add up all these omega values, you get an omega equal to 1, which means k is 0, which kappa is 0. That means we live in a flat Euclidean obeying geometry universe in a flat Minkowski spacetime. Now that really isn't the problem here. The problem isn't that we live in a flat universe. The problem is that we live in a flat universe today, because even the smallest perturbation of that omega value will deviate away from its original value and away from 1. As you can see here, in a universe where if it began with 1.02, then it would deviate away from 1 in a positive way and result in a positively curved universe. Or on the other hand, if it started with a 0.99, for example, it will deviate away from 1 into an open universe. So the fact that we live in a universe that is so close to 1 today means that the value was much closer to 1 yesterday and the day before and the billions of years before. And through that perturbation, we've arrived here today. So why, the problem is, the crux of the flatness problem here is that why was the universe's omega value so close to 1 before and so fine-tuned for flatness to exist? And despite the evolution of time, we still have a value so close to 1. And that's really a puzzling mystery here in the flatness problem in physical cosmology. And so from the shape of the universe, we then move on to the causality problem, which is the horizon problem. When we look back into the CMB, we can see patches of sky that exhibit similar physical properties. Now this is again deeply puzzling, because these patches of blobs of gas or galaxies or cluster of galaxies are so vastly separated in distance that even light couldn't take enough time in this limited time of the universe's age of 13 billion years to travel to the other side of this patch to exhibit similar properties. For example, the average temperature in the entire CMB sky is 2.7 Kelvin. There are anisotropies of 1 in 100,000, and these figures, these parameters, are not supposed to happen in a causally connected universe. So that's the homogeneous problem that we call the horizon problem. Here is a diagram illustrating everything I've just said. Two blobs of galaxies has its own particle horizon, beyond which it is causally disconnected. It cannot have any effect on it. Now, a really good way to understand this concept is using a space-time diagram. Here we can see the past cone of the Earth. Any system, any subsystem inside this cone is allowed to interact that can cause an effect that we see today. Anything outside this cone is, for example, this point here is said to be causally disconnected, because no matter what it does, no matter what shape or temperature or features it may have, it cannot shape the present today. And what you see here, which is the real puzzle of the horizon problem, is that points in the CMB themselves have their own past cones that do not intersect, and yet they have similar properties. A good analogy for that is how did the hot coffee and the cold milk knew at exactly what equilibrium temperature they're supposed to have, even before mixing and becoming coffee itself? How did they know what temperature to be in the first place is the fundamental problem of the horizon problem. So what is a potential solution? And that solution is inflationary cosmology. Inflation is an exponential expansion of space-time, occurred for a very, very, very brief short duration of time, between 10 power minus 36 to minus 33 seconds. That's incredibly small time period, and yet the universe expanded by 10 power 26 folds. What that means is, if it started off as a dime, then it is the size of the observable universe today. If it started off as the size of a proton, then it would become a dime, is what I'm trying to say. Now, this is possible by relativity, of course. When there's an energy density scalar field that travels down a potential hill, moving from a false vacuum to a true vacuum state, it's this transition that creates the energy required to expand space exponentially. Now, this transition is known as a slow roll inflation. It even accounts for reheating phase of the Big Bang theory that we see in the CMB. Now, this transition happens when the universe moves from a global maximum to a local minimum, or even a global minimum. So that is to say, inflation can happen more than once. The transition between the false and true vacuum state can also happen through quantum tunneling effects. So there are more than one process that it can happen. That's the motivation to say that it's possible, even if the odds are so small. So the result of introducing inflation to cosmology is that it solves all our cosmological problems like the flatness, the horizon, the magnetic monopole. It even predicts, and this is where inflation needs to be taken more seriously, because Any science theory that can predict something in the future is testable, is verifiable, and therefore needs to get more credence level attached to it. So it predicts temperature anisotropies in the CMB, very specific fluctuations. It promotes homogeneous large-scale structure to the universe. It promotes galaxy formation and evolution. And one thing I did not add in the slide is that inflation predicts the abundance of light elements like helium-3, for example. Now this is remarkable because inflation predicts on like specific patches of the CMB that helium-3 should exist here, and we point our spectroscopes to this patch of sky and we see helium-3. So that's again another huge predictive power that pushes inflation forward into a scientific theory that could, I guess, be published in undergrad textbooks soon. So in my report, before we publish them to undergrad textbooks, I evaluate if inflation is in fact viable, is in fact the mechanism of nature and not just the mathematical framework, which is a coincident to problems in Big Bang. I analyze empirical data and I see if I put a Bayesian approach to this data and outcomes inflation as the most highest confidence levels of theory, which is basic science practice to say. And again, I analyze predictions of inflation. But what really is my criteria in my report is the intrinsic problems. I'm calling these intrinsic problems because these problems wouldn't have existed without inflation's introduction in the first place. That is to say, if there was no inflation, then these problems wouldn't have existed. For example, the inflaton particle, any energy scalar field needs to have an associated particle with it. Although scalar fields are relatively new in physics, we did discover the Higgs field and the Higgs boson associated with it. So we expect an inflaton particle to exist in nature, and discovering this particle would push inflation forward. Then there's a fine-tuning problem. Why was the universe so specifically fine-tuned for this? Then there's the multiple theories problem. Theories such as the variable speed of light, FFR gravities, and things like string theory and things like that. All these theories, just as efficiently as inflation, solve the problems of the Big Bang cosmology. So why then do we give inflation the benefit of the doubt? Or why do we say inflation is the cosmological principle? And then there's the measure problem. Part of inflation talks about eternal inflation, where bubble nucleation of universes creates different universes, which is to say multiverses, and we are causally disconnected to those universes, and how can we measure the parameters and constants and features of those universes? So that's another problem. That's a constraint that I put on inflation in my report to say that, is this viable, is this feasible? But there is a silver lining, of course. The Euclid 2020 mission is going to measure the parameters of dark energy in a much more precise way, and we can use this data to verify predictions of inflation, for example. And of course, the CERN experiments that are moved to 13 TeV this year. But although the inflaton particle needs a much more higher energy density to measure this particle, so it isn't a right step forward by the CERN experiments. So that's something that I use in my report to say that it's possible, it's in the works, it's in the future. These are my references for you if you want to go through. And this slide here is to show the overwhelming support of notable physicists in support of inflation. But the important thing to note here is that there are physicists opposing it as well. So it's a good, healthy dialogue to have. So we also have we have two Nobel laureates on each side of the argument. Brian Schmidt, of course, got his Nobel for the discovery of dark energy. Rainer Weiss here is actually going to get his Nobel same time next week, this Tuesday, for his efforts in gravitational waves. There's Ed Witten, who is regarded widely by his contemporaries as the Albert Einstein of the 21st century. There's Steven Weinberg, who's the father of particle physics and the standard model cosmology. There's, of course, Leonard Susskind, Brian Greene, Sean Carroll, Stephen Hawking, Martin Rees, and everybody else. So in short, my report is about how viable is inflation, how seriously should we take this. And of course, I want to give you the answer in my report, but for now, I'll give you a soft answer. The answer is yes, with a giant asterisk beside it. That asterisk stands for pending investigation and scientific methodology and objectivity and data analysis before we actually say inflation is indeed the mechanism of how nature functions so close to the Big Bang. And indeed, thank you so much for listening. Yeah. I think